What I'm going to talk about in this video is something called the scalar product. Now this is a calculation we can do involving two vectors and the angle between them, and using their magnitudes to calculate various properties relating to these two vectors and the directions in the relationship to one another. Now when we're doing this, there's several key things we have to take into account and several key properties we have to remember. So let's set up the scenario. We're going to take two vectors and what they're going to be is positioned end to end. They're going to make an angle between them of theta. Now, first thing to remember is that the magnitude of the projection of B on A is given by the magnitude of B cos theta. So if we set up the scenario similar to this, there's my vector B, there's my vector A. Remember back to what we talked about when we were looking at projections. So at this point here, my projection of the vector B down onto A is the equivalent of me calculating the length from here to here. That projection, if we could use a bit of basic trigonometry, SOHCAHTOA, to find out that this length here is the equivalent of magnitude of B times cos theta. So that projection there comes in handy because what I'm going to do is I'm going to imagine taking the product of the magnitude of A times this part here, so times the magnitude of B cos theta. What we're going to do is we're going to take that and we're going to define it as what's called the scalar product. Now this is often referred to as the dot product, the reason being it's denoted by A dot B. Now this has several key properties that we have to be able to utilize and remember in order to do effective calculations involving this. Now the first thing is that A dot B is a scalar. The name suggests that without even thinking of it. It's called the scalar product. Of course it's going to give us a scalar. Second thing is if I take the scalar product of a vector with itself, so A dot A, that's the equivalent of doing magnitude of A times magnitude of A times cos of 0. There's no angle between a vector and itself. That gives me A squared. Cos of 0 is 1, so it's magnitude of A times magnitude of A, so A times A, which is A squared. I also need to remember it's commutative, so A dot B is the equivalent of B dot A, and it's also distributive over addition. So if I've got A dot bracket B plus C, so vector B plus C, that's the equivalent of doing A dot B plus A dot C. So I can add those two vectors and then take the dot product, or I can do my two dot products and then add the solutions together. Now this comes in handy when we're looking at finding angles between set vectors using some of the other properties. You'll see examples of that in the exercise video. One thing to remember is property 5. If A dot B is equal to 0, and neither A nor B are 0, that there's a key point. A and B cannot be 0. For this to work, the two vectors are perpendicular. Think about it. A dot B is the equivalent of magnitude A, magnitude of B cos theta. Now if it equals 0, but A and B aren't 0, magnitude of A and magnitude of B are both non-zero, so cos theta has to be 0. And for cos theta to be 0, theta has to be 90 degrees or pi over 2, which means that it's a perpendicular, i.e. there's a right angle between the two vectors. Look at the unit vectors in the x, y, z direction, so the I, j and k. If I were to do the dot product of each with itself, so I dot I equals j dot j equals k dot k, all of those would be the equivalent of 1. Remember in the three-dimensional system, I, j and k are all perpendicular to each other, so if I was to take the dot product of any of those two unit vectors, I would get 0 due to this fact. Now I've told you about several properties and I've told you about calculating angles, but what if I don't know the angle between the two vectors? All I know is the components of it. Well, we can calculate the scalar product using rule number 7. So we can say that A dot B, let's imagine that's the equivalent of the vector A1i plus A2j plus A3k, dotted with B1i plus B2j plus B3k. What I'm going to do is take the associated elements of each of them and calculate the product. I.e. what I'm going to do is calculate the product of the I elements, so A1, B1, product of the J elements, A2, B2, product of the K elements, A3, B3, and just add them all together. What I can also do is rearrange this formula that I've taken from the start, calculate the angle between the vectors, make cos theta the subject of the formula, and I know that I can calculate the angle as cos theta is equal to A dot B over magnitude of A, magnitude of B. It's a fairly simple property to work with and a fairly simple rule to do, and it allows us to do a few examples and a few different exercises where we can calculate properties with vectors in relation to one another. show you a couple of quick examples. So let's imagine I just give you two vectors, A and B, and I want to find the scalar product of them. Well, what that means is I want to find A dot B, and in order to do that, remember what I said, the I elements multiply together, the j elements together, the k elements together, and then I add up the solutions. So I'd have 2 times negative 3 plus 3 times 2 plus 4 times 0. So I'd end up with negative 6 plus 6 plus a 0, which is equal to 0 there. Now a quick thing you could actually say about this is that they're then perpendicular to one another. They're both non-zero, dot product is 0, so they're perpendicular to each other. Second example, let's imagine I want to find the scalar product of A and B. This time though I'm telling you the magnitude of both vectors, i.e. the length of them, and the angle between them. So this time, what I want to do is use the formula A dot B is equal to the magnitude of A times the magnitude of B times cos theta. So in this case, magnitude of A is 5, it's then going to be times 4, it's then going to be times cos theta, so in this case it's going to be times cos of 60. So that's going to then give me 20 times cos of 60, which is a half, so it's going to be 10. So my scalar product is going to be 10 in this case. I could also give you the vectors in component form in terms of the unit vectors I, j and k, and if I do that, I want to find the angle between them. In this case, I would still use the same sort of format. I would just have to remember I've written the vectors in a different way. So I know for the angle, cos theta is equal to A dot B over the magnitude of A, magnitude of B. So let's imagine I'm going to make this vector my A and this vector my B. I know that then A dot B, that's going to be equal to the i's, the product of the i's, so minus 8 times 1, plus the product of the j's, plus 4 times 2, which is equal to 0. Now I could say the angle straight away from this, but I want to get the magnitude of A and B and just confirm that it's going to be that case. So the magnitude of A is going to equal the square root of 1 squared plus 4 squared, which in this case is the square root of 17. Magnitude of B is going to equal the square root of negative 8 squared plus 2 squared. 8 8s are 64 plus 2, that gives me the square root of 68. Plug it all in here and I get that cos theta is equal to 0 over root 17 root 68, which just confirms exactly what I could have told myself from this stage, that theta, the angle between them, is pi over 2 or 90 degrees. We tend to work in radians here, so pi over 2 is fine. It may ask you for it in degrees, just remember that's 90 degrees. So there you go, some basic calculations involving this scalar product. We have to be able to do these and work with it, and we have to understand what it means with two vectors in relation to one another.